Alright, in this video we're going to take a look at some sample multiple choice questions that would help for studying for an electrochemistry test in grade 12 chemistry. These would also be helpful for AP chemistry, but AP chemistry questions generally go further and deeper as well. So the first question, which of the following is true regarding the voltaic cell described here using line notation? Pause the video and see if you can do this. So in line notation, we know that the first half of the line notation is the anode, and the second half is the cathode. We don't have to look that up. We just know the anode always comes first when you describe a cell using line notation. That means the magnesium is being oxidized to make magnesium 2 positive, while the tin 2 positive is being reduced to form tin metal. So I'm taking magnesium electrode and forming magnesium 2 plus. So magnesium is going to be a reactant, magnesium 2 plus a product. Over here, we're taking tin 2 positive and reducing it to make tin. So tin 2 plus is a reactant and tin is a product. Which of the following is true? The magnesium electrode gets heavier while the magnesium is being oxidized, so it's a reactant becoming magnesium 2 positive. Because the magnesium is a reactant, it's actually going to decrease over time. Excuse me. Its mass would get smaller. The tin concentration would increase over time. Well, again, over here, tin 2 plus is being reduced to make tin, so tin 2 plus is a reactant. Its concentration is actually going to decrease over time, not increase. Cations flow from the salt bridge towards the tin half cell. Well, the tin half cell is the cathode, and we remember that cations are attracted to the cathode. Anions are attracted to the anode. So that actually looks pretty good. The salt bridge contains a salt solution with cations and anions in it. It completes the circuit within the cell and prevents the buildup of charge in the two half cells. And finally, electrons are flowing from tin to magnesium. Well, the magnesium electrode is where the oxidation is occurring, the anode, so it's where electrons are being lost. And they're going over towards the tin electrode where reduction is occurring, electrons are being gained. So no, the electrons are not flowing from tin to magnesium, it's the other way around. Question 2. Try that question yourself. So which of the following species is most easily reduced? Most easily reduced, another way to phrase that is that it has the highest reduction potential. So I'm going to look on my chart of half reactions. Hopefully you've got one with you. If not, pause the video and go grab your data booklet. I'm looking for the most easily reduced substance. Things that are being reduced are on the left-hand side of this chart. We can tell that because each substance here is gaining electrons. Gaining electrons is reduction. So if I'm looking for the thing most easily reduced, it has to be on the left side of this chart with the highest reduction potential, these numbers over here. So it has to be on the left side and highest up. So looking at the choices, copper 2 plus is a possibility, it's right here. Gold 3 plus is a possibility, it's on the left and it's higher than copper, so gold right now is my best choice. Zinc is actually down at the bottom of the table and it's on the wrong side. Zinc is on the right hand side, so zinc actually would not be reduced. Silver cations could be reduced, they're here on the left side of this equation, but they're actually below gold, so silver has a lower potential than gold. So gold 3 positive was the one that was most easily reduced. It had the highest reduction potential. Number 3, which of the following species is the strongest reducing agent? So a reducing agent, we know, is a substance which gets oxidized. So on this chart of reduction reactions, the reducing agents are found on the right-hand side. When you read the equations backwards, they are being oxidized. Now, if I want the substance which is the strongest reducing agent, then I want the substance which has the highest oxidation potential. So strongest reducing agent would be most easily oxidized, right? Because the reducing agent is the substance that is oxidized, so it has to have the highest oxidation potential. So on my chart, things being oxidized are on the right-hand side, and remember these numbers are actually reduction potentials. When you read the equations backwards for oxidation, we change the sign of these numbers. So the largest oxidation potentials are actually near the bottom when these numbers get changed to positive numbers. So I'm looking for something on the right-hand side of this chart near the bottom. So looking at those choices, the best answer looks like it's going to be one of the sodiums. Now, sodium is right near the bottom on the chart, but I want the thing on the right-hand side, so it's going to be sodium metal, not sodium cation. So sodium metal can be oxidized, and its oxidation potential would be positive 2.71 volts. Which of the following would be capable of reducing lead 2 plus to lead? Now there's a long way to do this and there's a fast way to do this. I'll do this the long way for this one question, and then we'll do it a shortcut way in the next couple. So the long way would be to say if I want lead 2 plus to be reduced, it's going to gain electrons to make lead. I'm going to look at my table of reduction potentials and notice that lead 2 plus being reduced to lead has a voltage of negative 0.13 volts. So its reduction potential is negative 0.13 volts. What I want is a substance to go with this that will be oxidized. If the lead is to be reduced, we need something that will be oxidized. And when the reduction potential is added to the oxidation potential, we need the cell potential to be a positive number. Okay? When the cell potential is positive, it means that the reaction is spontaneous. It has a very large equilibrium constant, and so yes, the lead would be reduced to lead metal. If the cell potential turns out to be negative, then that reaction would be non-spontaneous. It would have a tiny equilibrium constant, and the reaction would not work. So we need something that can be oxidized. Things being oxidized, we remember, again, are on the right-hand side of this chart. So looking at these choices, things we can rule out right away. Bromine is not going to be oxidized. If it were to lose electrons, it would become positively charged, whereas bromine, we know from grade 11 chemistry, becomes Br negative. So Br does not get oxidized. Another one here that does not get oxidized, it's not on your chart on the right-hand side, is the magnesium ion. Mg2 plus is already oxidized, so it will not lose any more electrons. So Mg2 plus is not found on your chart on the right-hand side. B and C, chloride and zinc, can both be oxidized. If you look on your reduction table, chloride is near the top, and we read this backwards. Chloride can be oxidized to chlorine gas. And zinc is down here. Zinc can be oxidized near the bottom to form Zm2+. Of those two, the higher oxidation potential was zinc. So I'm going to start with that as a guess. Zinc, if it gets oxidized, becomes Zm2+, loses 2 electrons, and its oxidation potential is positive 0.76 volts. Now notice when I add those together, I'm going to get a positive cell potential, which means that this was the right answer. Zinc being oxidized is the best choice. If we look back at the other possible answer there, chloride's oxidation potential would have been negative 1.36 volts. If we had put negative 1.36 volts here, we'd get a negative cell potential, which means the chloride ion would not have been able to reduce lead. So that's a long way of doing this. It's to calculate the cell potential and look for the cell potential that's positive. The faster way to do it is to realize that we were wondering right there, what would be able to reduce Pb2 plus to lead? Well, on my chart, Pb2 plus is right here, and I want it to become lead. That means I need to react the Pb2 plus with something on the right-hand side of the chart. The lead is going to be reduced. We need something to be oxidized. Now, we just saw the answer is zinc. And if you notice, it establishes a pattern that when something on the left reacts with something on the right below it, we ended up getting a positive cell potential. When something on the left reacts with something on the right above it, the chloride ion was way up here above the lead, we ended up getting a negative cell potential, and that's a non-spontaneous process. So the fast thing to do is just to look for this pattern. Something on the left will react with something on the right and below it, or something on the right will react with something on the left above it. When you have that pattern on this chart, you'll end up with a positive cell potential, and the reaction will be spontaneous. See if you can use that same reasoning for question number 5, but this time we'll avoid the long way of doing this and just use that shortcut method. Which of the following could oxidize Fe2 plus to Fe3 plus? So you look on your chart and you find Fe2 plus and Fe3 plus, and it's this equation right here in the middle of the chart. I want something that can take Fe2 plus and convert it to Fe3 plus. Well, by the pattern we just established, since Fe2 plus is on the right-hand side, it will react spontaneously with things that are on the left side and above it. So I'm looking for anything on the left and above it to react with the Fe2 plus. Looking at these choices that we're given, the best choice there, chlorine, is above and to the left of Fe2 plus, so Cl2 is the best answer. And one more time, use the same reasoning. Which of the following would be able to reduce tin 4 plus to tin 2 plus? So again, you look at your chart, you find tin 4 plus with tin 2 plus, and that's this equation just above the halfway point. And we're looking for something to reduce the tin 4 plus. So here's tin 4. It's on the left side of our table, so by the same pattern, it will react with something on the opposite side, on the right, and below it. So looking at the choices that we were given, nickel 2 plus, nickel 2 plus, well, nickel 2 plus, nickel is below the tin, but the nickel 2 plus is on the wrong side, so that's not a possible answer. Manganese, Mn, is on the opposite side and below, so manganese looks like a good choice. Bromine is above our reaction, and the gold is also above, so the manganese was the best choice. Number 7, can you take that same logic we've been using and apply it in this way? We have 4 solutions, different nitrate solutions, and we want to store them in copper vessels. So which of these solutions should not be stored in a copper vessel? See if you can reason this out. So the copper vessel obviously contains copper metal. It's made of copper metal. And the reason you wouldn't want to store a solution in it is if that solution were to chemically react with the copper. That's the underlying idea here. Looking at these solutions, they all contain nitrates, so we'll assume the nitrate is not an important part of this. The first one contains Zn2+, the second one contains aluminum 3+, the third one contains sodium positive, and then silver positive. So we're wondering which of these would we not want to store in our copper vessel. It would be the one that would react with copper. So looking at our choices, we find copper. Copper on this chart is right here. It's in the middle of the chart on the right-hand side. So what would react with copper? Anything on the left-hand side and above it. So looking at those choices, the zinc looks like it would be okay. It's on the right-hand side, but below it. The aluminum is also okay. It's on the left-hand side and below it. The sodium is also okay on the left-hand side and below it. But the silver looks like it's a problem. Silver is on the left-hand side of the chart and above copper, so the silver ion would react with the copper. So because the silver would react with copper, you wouldn't want to store the silver nitrate solution in a copper vessel. Number 8, which of these is the strongest oxidizing agent? Again, strongest oxidizing agent. The oxidizing agent gets reduced, so we want the most easily reduced, and that means we want the highest reduction potential. That's my reasoning. So looking on the chart, things that get reduced are on the left-hand side. That's why it says at the top, these are the oxidizing agents. And I want the one with the highest reduction potential. So looking at those choices, chlorine jumps out as the best choice. Number 9, which metal below would not dissolve in hydrochloric acid, producing hydrogen gas? Pause the video and see if you can try that yourself. So you remember hydrochloric acid is a strong acid, and that means it contains hydrogen ions and chloride ions, and it ionizes completely. It's forming hydrogen gas because the hydrogen ions are being reduced, and there's the hydrogen gas being produced. So we're wondering which of these metals would not react with hydrochloric acid and produce hydrogen gas. Then to reword that, which of these metals would not react with the hydrogen ions to produce hydrogen gas? Looking at the chart, hydrogen ions from the acid are here on the left side of the chart, so they will react with metals on the right below them. So some common metals that would dissolve in hydrochloric acid, things like magnesium and zinc, they dissolve in hydrochloric acid. But things on the right and above would not dissolve in the hydrochloric acid in that way. So silver metal would not dissolve, gold metal would not dissolve, things like that. So looking at these choices, would not dissolve, well, we just saw zinc would dissolve, magnesium would dissolve. Looking at the chart, nickel is also below and to the right, so nickel will dissolve. But copper is to the right and above the hydrogen ions. Copper is the one that does not dissolve in the acid. Number 10, which of these electrochemical cells would produce the largest voltage? These are all standard cells. The concentrations are 1 molar of the solutions, and we'll assume they're operating at 25 degrees Celsius. So I hope you didn't go through each one and calculate the voltage produced. That would be a long, very long way to do this. When you're calculating the potential, the voltage in a battery, in a voltaic cell, you're calculating the potential difference between the two electrodes. So if you want the largest voltage, you want the largest difference of potential. So that means you want to choose electrodes that are far apart on the chart. So essentially, I'm just going to look for which pair of electrodes of the choices are farthest apart on this chart. The difference in their potentials will be the largest, and they'll have the largest voltage. So of these choices, I'm looking for zinc and copper. Well, zinc and copper, gotcha. They're not that far apart. Magnesium is very near the bottom, and gold is very near the top. Magnesium and gold are actually quite far apart on the table. Lead and silver, they're not as far apart as the magnesium and gold, and copper and gold are also not as far apart. So magnesium and gold were the farthest apart on the chart. They're going to produce the largest voltage. Number 11, which reaction below is spontaneous? Well, again, that's that same concept that we were just discussing. To be spontaneous means it will produce a positive cell potential, and we know that positive cell potentials are produced when you have this pattern, something on the left reacting with something on the right below it. So I'm just going to look here and says, when nickel reacts with silver ions, nickel is right here, it's on the right-hand side. Silver ions are up here and to the left. So silver and nickel reacting, that should be a positive cell potential, and therefore it should be a spontaneous reaction. Just to look at the other one, copper reacting with tin 2+, well, copper is here on the right, tin 2+ is below it to the left, so that would not be a spontaneous reaction. It would have a negative cell potential. So if you looked at the other options, you'll see they also have negative cell potentials. They're non-spontaneous. Number 12, what is the oxidation state of sulfur in the metabisulfite ion S2O5 2 negative? Well, we know that oxygen's oxidation number is -2, and there are 5 oxygens in the formula, so 5 times -2 is -10. The entire ion is -2 charge, so if we have -10 from our oxygens, and we have to have -2 overall, then there has to be +8 on the 2 sulfurs. Right? -10 and +8 would give me -2 overall. But that +8 is divided over 2 sulfur atoms, and we'll assume that they're the same, so each one of them ends up being +4. Okay, 2 more questions here. Number 13, when this redox reaction is balanced in acid solution with smallest whole number coefficients, what will be the sum of the coefficients in the reaction? So this is a little bit more involved. Pause the video and see if you can balance that reaction in a acid solution. So the way we learned this in class was to split this into 2 half reactions. Permanganate becomes manganese 2 positive, and chromium becomes chromium 3. And then we went through a bunch of steps for balancing this. You might remember, balance everything except hydrogens and oxygens, and then balance the oxygens by adding water, balance the hydrogens by adding hydrogen ions, balance the charges using electrons, make the electrons equal by multiplying the equations by coefficients, and then recombine the equations. And we could do all of that right here, but again, we have this chart. And if you notice, up here, there's permanganate becoming manganese 2+. The half reaction is right there. So I actually don't need, for this multiple choice question, to go through all that work I just described. I could just copy this equation. Permanganate plus hydrogen ions, 8 of them, and 5 electrons becomes manganese 2 and 4 waters. So that's copied right off of the chart. In the same way down here, chromium and chromium 3, well, that's pretty easy to balance, but you could also just copy it off the chart. And there we go. And now all I need to do is recombine the equations. Well, the first one has 5 electrons and the second one has 3, so I'm going to end up multiplying the first by 3 and the second by 5 to make the electrons equal. They'll both end up with 15 electrons, and the electrons will cancel. So looking at the final reaction, we'll end up with 3 permanganates, 5 chromiums, 24 hydrogen ions. We'll end up with 3 manganese 2 positives, 5 chromium 3 positives, and 12 water molecules. Maybe just double check your charges to make sure that they work out. 3 negatives and 24 positives, the left-hand side is positive 21. 3 times 2 is 6 positives, plus 15 positives. The right-hand side is also positive 21. I'm pretty sure I've done that right. So now I just add up the coefficients. 3 plus 5 is 8, plus 24 is 32, 35, 40, 52 is the answer. Now in this equation, we're asked what is the reducing agent in the reaction. Well, the reducing agent is the substance that is being oxidized. So if we put some oxidation numbers in here, the manganese in permanganate has an oxidation number of plus 7. 4 O's is 4 times minus 2 is negative 8, and then the entire thing was negative 1. So manganese is plus 7. Over here, manganese is plus 2. So the permanganate is being reduced. But I'm looking for the substance that was being oxidized. The reducing agent is being oxidized. The chromium starts with an oxidation state of 0 and finishes with an oxidation state of positive 3. So the chromium went from 0 to 3. It lost 3 electrons. Well, then chromium was being oxidized, and so chromium, Cr, is the reducing agent. Remember that the reducing agent, the oxidizing agent, the substance being reduced, the substance being oxidized, they have to be reactants. They won't be products. So you could just ignore anything here that was a product. Okay? All right, I hope that helps. A little bit of review for your electrochemistry test, or perhaps studying for the electrochemistry portion of your final exam.